Hi, in this video, we use this result on screen from my previous video to give a second proof of the area formula. This proof will come more natural and more intuitive to those who were already familiar with a little bit of manifold stuff. And this proof is saying that the area formula holds for Lipschitz maps because it holds for C1 maps. And it holds for C1 maps because of the well-definedness of the surface measure, which is ultimately a consequence of the u-substitution formula for integrals. If you see my previous video, you know what I'm talking about there, but this video focuses on giving a proof of the area formula using this equality of surface measure with the Hausdorff measure. I begin with a corollary of this theorem, and that is if f from u into this manifold is a local C1 parameterization, then for every a subset of u measurable, the set f of a is measurable, and hn measure of f of a equals integral over a of Jacobian df of x dln of x. Okay, let's see what is going on here. Because isn't this integral Jacobian just the mu of f of a, so that it is already in the theorem? Well, the answer is no, because of the technical requirement that in the theorem we need a to be Borel. And that is because that is needed for mu to be well defined in the first place. So if f of a was Borel, then this would be immediate from the fact that now f of a is Borel, so that this is defined, and by the theorem this is equal to hn of f of a, and by definition this is integrate Jacobian over the preimage of the set. So preimage of f of a is just a. Okay. For arbitrary measurable a, we use one of the tricks that we've used many times. We write a to be k union of z, where k is a countable, at most countable, union of compact sets, and z is a null set. And that is always possible for a measurable subset of Euclidean space. Now, hn of f of z is 0. And I've done this many times, so I'll leave it as an exercise. And f of k is Borel, because it is also a union of compact sets, simply from continuity of f. Thus, hn of f of a equals hn of f of k, which is now a Borel set, so that it is equal to mu of f of k, and that makes it equal to integral over k of Jacobian of dfx dln of x But guess what? I can add back the null set z, because the integral over that is just 0 and doesn't change anything. And that's the end of the proof. So we have this corollary, and this corollary is basically the area formula, but for one-to-one C1 parameterizations. That means also the rank of the derivative is equal to n everywhere. But that will play a key role in the proof of the area formula. So proof of the full area formula with multiplicity function and everything. Okay. A is a subset of Rn measurable. So the setting, recall, is that F is Rn into Rm is Lipschitz. And A is a subset of Rn and measurable. Okay, we want to prove the area formula equality here. Let A1 be the set of those x's in A where derivative of f of x exists. By Rademacher, it happens almost everywhere, and rank of this is equal to n. A minus A1 is union of a null set where the derivative does not even exist, and the critical set where rank is less than n. Okay, the null set maps to the null set, to a null set by just Lipschitz estimates, and by Sard's theorem, and that null sets map to, well, here we mean Hn null sets, we get that Hn of f of a minus a1, and we had seen this before too, is 0. So that means the critical set plus every other garbage set does not produce any significant set in the image. On the other hand, they don't contribute in the domain either. So Jacobian of derivative of f of x, which is one side of the area formula, so we want to integrate this over A, equals integral over a1 of Jacobian df of x, dln of x. Because Jacobian over the critical set by definition is 0, and the null set doesn't contribute anything either. Maybe, well, let's not assume that everyone has watched the video, the previous proof of the area formula, and let's add some more details here. So when this is 0, it follows that the function, multiplicity function, is equal to the multiplicity function over a1 for Hn almost every y in the target space. And this is because these two can be different only if y belongs to this set. And that set has 0 measure by this. So if we prove that this is measurable, Hn measurable, we will have proven that this is Hn measurable, and also that integral of the multiplicity function Hn over Rm is just the same as integral of a1 y dhn. So once we show that fa1y is Hn measurable, so that these integrals are well defined. Okay, so if we then prove that this quantity is equal to this quantity, then we will have proven that this is equal to that. This is the original area formula we want to show, and by these reductions we only need to do this. So all of this is saying one thing. So without loss of generality, we well, that's not the right word, so we only need to prove the area formula for A1. Okay, so what I wanted to say is that without loss of generality, A equals A1, but there's so much we did to get rid of the A minus A1. But anyway, so what happens on A1, and how are we going to use this equality of surface measure on manifolds and that? And where is a manifold anyway? And here is where this amazing C1 approximation of Lipschitz maps comes in. So, and that was one of the videos we dedicated to. By C1 approximation result, A1 is okay, let's say there are measurable, of course, AI such that the union of AI covers A1 up to a null set, which we again throw away by all the above. And so what is special about these AIs? For every I, there exists a map G from Rn into Rm that is C1, and F equals with G, derivative of equals with dg on the set AI. So we had talked about this in the C1 approximation video. So we can exhaust the set A1 by subsets on which F coincides with the C1 function. From the inverse function theorem, each AI is union of subsets let's say Aij such that G is 1-to-1 on an open set Uij containing Aij. So it's not exactly inverse function theorem because we map between separate dimensions, but once you restrict to a certain projection in the bigger space, it actually becomes an inverse function theorem. It's a beautiful exercise in advanced calculus that if you have a C1 map even into a larger space and rank is full, then in a neighborhood it's 1-to-1 and invertible from that part actually. What is happening is that here is AI, and we know that G is C1, and the rank of derivative of G, which is rank of derivative of F, is equal to n all over this set. Therefore, every point has a neighborhood on which G is 1-to-1. So every point has that, so we can decompose AI into at most countably many pieces on which this happens. So relabeling and stuff like that, or maybe just let's keep this notation, okay? There's nothing wrong with that. Now observe that G of uij, this open set, is an embedded submanifold, C1 submanifold, with G being a local parameterization itself. And that is the manifold we will apply this equality of surface measure to, with Hn to. Okay, so for every I now, for every j, before that, let's see what has happened. Observe that A, which was union of AI, is now a union of aij's, union over I and j. So for every I, and we can assume these are disjoint. We can assume these, that means aij's are disjoint. Can always do that, even postpartum, after everything has been done, we can do exclusion inductively. Okay, now for every I and every j, what we know is that Hn of f of aij is equal to Hn of g of aij. Why? Because aij is a subset of ai, and on ai, f coincides with the C1 function gi. Okay, so this, I meant gi. And now we know from this equality, so this by definition is mu. Okay, it is not, but this is why we proved actually the corollary, because aij is only measurable, so gi aij is not necessarily Borel, so I don't want to write. So the whole corollary was to avoid having to write mu here. But what we have proven was that this is integral over aij of the Jacobian of the parameterization dgi at x d ln of x. Now I can write this as integral over aij of Jacobian of df at x d ln x. Why? Because on aij, in fact on all of ai, f agrees with gi. Okay. Now each f of aij is Hn measurable. We've done this before, but once more, you write aij, because it's measurable, as union of compact sets plus a null set. The null set goes to an Hn null set, and other sets go to compact sets. So image is also union of compact plus an Hn negligible set. So it becomes an Hn measurable set. So the function nfa1y, the number of points from a1 which map to it will be, because aij's are disjoint and f on each one of them is 1 to 1, this is just count how many of f of aij's contain y. So if you do summation over aij of characteristic functions of images, this is exactly the multiplicity function. So this is an Hn measurable function, because each characteristic function is Hn measurable by this fact. So we can integrate it Hn, so integral over Rm of the multiplicity function against the hn becomes just summation I over j, I and j of hn measure of faij. But from above, I have actually computed hn fij, and that becomes summation ij integral over aij of the Jacobian derivative of f at x dln of x. But aij's are disjoint, so this becomes integral over union of them, which is only a null set shy from being all of a1, which we can forgive and put this. And that looks like a familiar formula, the area formula for a1, and we had shown that that is sufficient to give the area formula for all of A. And that, ladies and gentlemen, is the second proof of the area formula. Hope you enjoyed that as well. Okay, so once we completed the proof of the area formula, the previous proof, we then talked about some corollaries of area formula. And here too, this new method that we've done produces some new consequences of the area formula, but I want to put them all together in a separate video that will come soon. So any questions, any complaints, please put them in the comments. If you like the videos, please also physically click on that like button, because unfortunately we have to make algorithms happy as well as humans. Thanks a lot for your attention, and see you in a future video pretty soon. Don't forget that I put the PDFs of these notes in the description. Thanks a lot and stay safe.